This video is coming out later than I would have hoped when the paper It came out 31st of December, so like a month ago. I still think it's good to kind of go over and talk about. It's a very annoying paper to read. I mean, you look at the front page and it's very, like, pretentious, I guess. That's what I would say. Like, they have this quote here and they have this stupid text here. So they make it seem like it's this big new thing that's coming out. And you look online, Transformers 2.0, it's the next big thing. And you read the paper, and first off, the cool ideas that are explained pretty well kind of stem from like learning to test at test or learning what's that paper called? It's learning to learn at test time, which came out like a year ago, I think. And they kind of make it seem like they came up with it. Like they do mention that. I think they mention that it came from this learning to learn at test time, but they make it seem like they developed the method, which is kind of, I don't know, it just feels wrong. And then then they add on to that, which I do think is cool, and I think it's interesting, that part. But then the actual architectures, they don't explain very well. Like the cool architectures that they kind of come up with, the architectures they call Titans. So yeah, I don't know. Some big complaints with this paper, I guess. Call me out if you want. I don't know. There's just something about this paper that they're not Transformers 2.0. Anyways, I'm gonna stop ranting about this paper and how annoying it is. I just don't like how it's supposed to be the next big thing. So yeah, let me get into the actual content. So I'll start with kind of linear transformers, learning to learn at test time, and then I'll go into kind of how they improve upon it. So like we all know normal transformers, they're quadratic, and you basically have this KV cache where your KV cache is equal to, so if this is our cache for K, it's equal to the size S by D. So you basically increase it by one token every time you add a new token to your sequence. So it increases it linearly with time. And you have this quadratic bottleneck with normal attention due to the softmax, and you have to compute this big matrix here, which is S by S. And you have things like flash attention, which kind of help with this, but you still have to eventually compute all S squared parts of your matrix, unless you have your mask here, which means you only have to compute this part. But anyways, you still have this quadratic complexity in terms of your algorithm. Now, linear attention basically takes this and it makes it, well, linear. And it does that by removing the softmax part and replacing it with some kernel. And almost everything can be, like if we have our normal attention here, so we have our output is equal to the softmax of our queries multiplied by our transposed keys multiplied by our values, where you basically have your linear KV cache. That's not a V, D. We'll call this our KV cache, which increases with the sequence length. Linear attention can basically be broken into Q, K transpose V, and then you add your mask as well. I should probably add the mask, softmax of Q, K transpose multiplied by the mask, multiplied by V, and O of the queries multiplied by the transposed keys, multiplied by the mask, then multiplied by the values. Since we're dealing with text here and temporal sequences, then you have your mask, where the KV cache is essentially compressed into a single D by D matrix. If you have multiple heads, you actually have H of these, where H is the number of heads, and you do that via an outer product. So let's say we remove the mask, then you do it via the outer product of your keys and your values here. I'm not going to go into too much detail because I've covered transformers, and I've gone over transformers and linear attention quite a bit. Too much, maybe, especially on linear transformers, and I'm hoping not to do it. I'm hoping not to cover linear transformers a lot in the next couple of weeks. I'm hoping to kind of do more. There's just been a lot of cool linear transformer papers that have come out. So yeah, this is kind of what it boils down to, where this is kind of your KV cache here, K transpose V. So if you add the mask here, then this is more annoying to compute, and I'll talk about later, like I've talked about before, you kind of block it. You can either have this as an RNN, or you can have it as the quadratic matrix, or you can block it. I think I talked about that in the last video, but this is what you have. You have either a linear cache, which has no compression, or you have this cache here, which is kind of this additive compression, where your hidden state at time t here is equal to the hidden state at time t minus 1 plus your keys, the outer product of the keys and the values here. So if this is your keys at time t and your values at time t, this would be a d by 1 multiplied by a 1 by d matrix. This gives you d by d. And your output at time t is the projection, the inner product of your queries. So this would be 1 by d multiplied by your hidden state, d by d at time t, and this gives you your output here. One can think of this as an RNN for every part of your sequence, while one can think of this as a single RNN going over your entire sequence. And when I say an RNN, I mean a unique RNN. Because technically you can do an RNN over your entire sequence for every token, just like you can here, but it's not unique, so there's no reason to do that, and the expressiveness is not the same between these two. So these are the two kind of methods that have been going around for a while. Can we make something that's as good as some linear attention mechanism that's an RNN as good as softmax attention? So far, we have found, like the research community, that linear attention kind of it's not as expressive as softmax attention. For example, the needle in the haystack task. You basically have to, like if I have some big sequence of text, I have something I want it to memorize, some big sequence of text, and then I say, like, give me the thing that was memorized. Then you basically the model has to know whenever it sees this thing, it has to know to store it in the hidden state. It has to know to not store this in the hidden state, not store this, and then it has to know, I need to extract that. But it doesn't know to store this necessarily, because it doesn't know what to store yet. While a transformer can say, I have the entire sequence, I'm just going to go and grab this part of the sequence. While hidden state has to know, in the future I need to store this. So yeah, it's not as expressive, and you run into these issues. Now, learning to learn at test time kind of is a middle area that is kind of weird. Like it's an RNN, but it uses this weird loss function gradient to update the hidden state here. So let me talk about that. Basically, what you have is you have your query key and value projection, and you update your hidden state based off this loss. So we'll define our loss to be equal to the L2 norm of some function. We'll just do a normal matrix multiplication, but you can make this kind of an MLP. In Titans, they call it MT. In the learning to learn at test time, they called it W, I think. But essentially your queries, I think it's queries, no, keys. So MT multiplied by your keys at time t, times MT minus VT squared. So this is just your normal L2 loss here, your reconstruction loss. And what you do is you say, all right, so I have my model or my weights at time, this would be t minus 1 actually. So at time t minus 1, and I update my model at time t minus 1, my inner model at time t minus 1, by by this gradient descent formula. So I'm basically saying I have this reconstruction loss that I want my model to optimize in this inner loop. So the keys and the values are a token at time t, so that's some token in your text that you want it to kind of compress into this hidden state here. And instead of just doing this additive formula that you do in a normal RNN or in a normal linear attention mechanism, you're going to update it. So instead of just doing plus the outer product of the keys and the values, we're going to update it via this gradient descent formula, where we are taking the gradient of our loss function here. So gradient of L, let's add a learning rate here. Gradient of L, we'll say the learning rate is also time dependent, and it'll be I'll just write it like that. I guess you also give it the model at time t minus 1 and x at time t, or kt and vt. And you do it with respect to the model parameters. So you take this, you're updating this part. Then once you update this hidden state, you need your output formula here to get, and they kind of said this is like, I think it was like an inference kind of procedure. But basically all you're doing is you're projecting it on, to the output. So O at time t is equal to your keys, your queries at time t, multiplied by mt here. So this is kind of your compression of your keys and your values. It's just updated by this, your gradient formula here, instead of just this normal, easy additive formula here. Now, the way this is optimized, kind of looking at this as an inner and outer loop, is your model. So whenever I say model, I mean we have a big transformer model that is taking in some text and it's outputting kind of the next token predictions. That model, the model that wants to do next token predictions, is doing, it's optimizing these parts here. So the value, the keys, queries, and the values. Basically, it has these weight projection matrices that are projecting x at time t to the queries, the keys, and the values at time t. So as you would expect. Now, what they kind of say is, oh, this inner model is being optimized here. Like, it's not being optimized by the outer model, the model that wants to learn text. This inner model here is being updated by this gradient here. So this inner model, MT, where I'm just making this a weight matrix. Like I said, you can make this an MLP if you want. This model here is kind of, it doesn't care about the outer model task. It's just learning this reconstruction task here. So the outer model basically corrupts this input in some way to force this inner model to learn this reconstruction, or since this inner model is optimizing this reconstruction task, it's kind of giving the model the information it wants to store in this hidden state implicitly by this reconstruction task. And what they kind of say at, like, in the Titans paper is, oh, something that is more surprising, the outer model will, or the inner model will hopefully store more of it in its hidden state, versus something that is less surprising, it won't store as much because the gradient will be lower, because this reconstruction loss will be lower. So that's kind of the intuition behind that. But basically it's this outer model giving the inner model the keys and the values to kind of have it optimize this inner model in some way to, I guess, help itself. But it's basically just you replace the additive rule with this gradient rule here, instead of it just being this naive outer product with the keys and the values. Now, if we look at the Titans paper, they take this idea and they add momentum to it. So let's go over to the Titans paper. Where is it? Down here. So they say here, they say MT is the model. Like I said, MT is just it's some model that you want to that you want the inner model to be. This is just going to be the model that learns this reconstruction task that basically is your hidden state, but it's this model instead. So you're optimizing this reconstruction loss with this inner model. So I just made it a weight matrix here, but you can make it an MLP. But if you make it an MLP, it's a lot harder to optimize in parallel. So this is what I wrote over here. You have your model at time t-1. So given some set of tokens and then given a new token here, it updates itself after it sees this new token via this reconstruction loss here, which is what I showed right here, and the learning rate theta t. And they say this is the surprise. So this loss here, and they're saying the loss is modeling the surprise, and the loss is just the reconstruction loss. So they start by adding this momentum term here. So instead of updating it directly with the gradient, the model, so instead of updating the model directly with the gradient of the loss, the reconstruction loss with respect to the model, so instead of optimizing this inner model, they optimize it using a momentum term. So the model at time t is updated by s at time t, and s at time t is this momentum update. So this is what we had initially here. So this is just our gradient, and this is our momentum term here. So that's all it is. It's just momentum. I forget what they say here. They say we break the surprise metric into past surprise, which measures surprise amount of very recent past, and momentum or momentary surprise, which measures the surprise of incoming data. So they say this is the instantaneous surprise, the surprise of the current token, while this is the decayed surprise here. So it's basically this moving average where this is your past surprise decayed by this parameter here, and your momentary surprise, your instantaneous surprise. So how are you going to update it controlled by this parameter here? And you update your model using this momentum term instead of just the instantaneous gradient. So kind of less noise that so this will remove kind of some noise, I guess, and momentum in general helps optimization. Get out of local minima, and it's just better in general for optimization tasks. And these parameters here are optimized by the outer model. So this is another parameter. So we have the queries, keys, and values. Now we have these two parameters here, kind of the momentum and learning rate parameters. They again add on to it. They add on another term here. So this is just the exact same formula that we had above, except they have this here, which is a forget gate. Or it's just kind of a moving average of the momentum gradient. So you can think of it as a forget gate by saying, oh, instead of just having this, whatever our model parameters currently are, we're going to, if this alpha parameter is a sigmoid function, then this controls how much of the past model we want to keep, or it's just a moving average of the model that we have. That's another way you can think of it. So this is what they end up with, and you're basically updating the model with this momentum term instead. But it's the same idea. You have this inner model that's being updated via the gradient of this loss function, where the loss function is controlled by the outer model, the model that wants to learn this this next token prediction task. And yeah, that's basically what they change, just this momentum part. So I kind of want to draw this out to show how they're different in some ways. So this is the hidden state update for linear attention here. So the hidden state update is we take a hidden state, which is a D by D matrix. We have our query key value projections here for a token. We do an outer product. This is the keys transposed at time t multiplied by v at time t. So outer product, which gives you your hidden state update. And so in Mamba 2, they have, you usually apply a mask. In Mamba 2, and the mask can be thought of as this parameter that you can control. And usually it's just ones. But in Mamba 2, they said, oh, why don't we make the mask some different value? So this can actually be some parameter here, p at time t, which controls, it's just this multiplicative factor of this input. But it's essentially just this additive procedure. So you have your hidden state, you add the key value outer product, and then you do your output projection and you get your output token. So this is really simple, just an additive RNN. They claim, and in general, you need a forget procedure because basically you're just adding. There's nothing to control the magnitude here, and you run into issues. You run into issues where the magnitude of this hidden state is going to blow up because there's nothing controlling this hidden state. If the model wants, it can just say, oh, I should continue adding to this hidden state. Why wouldn't I want to continue adding to this hidden state? Of course, I want to store as much information as possible, but you run into stability issues, and yeah, this runs into problems unless you add normalization and stuff. So we're basically going to take this part here, and we are going to replace it with the gradient update rule. So forward here is basically the outer product and inner product that we have over here. So there's the outer product and inner product here. So notice this is the outer product just with the keys and the values. It has nothing to do with the hidden state. And this inner product is directly with the hidden state in the queries. We're basically going to kind of add a function here that interacts with the keys and the values and the hidden state before it updates the hidden state. So we have our keys and values here, like we did before, but this forward method is going to be on the keys. So we're doing this forward method, and the forward method is just a matrix multiplication in this example, but like I said, it can be an MLP. So basically, you're doing an inner product with the keys and our weight matrix here. So this gives you an output, and you do your reconstruction loss here. So that's just the loss I showed over here. And you get your gradient with respect to the model. So this is your hidden state update here, which is just your gradient with respect to the model parameters. And you basically do the exact same procedure here, where instead of adding, you're subtracting because you want to minimize the loss. And you have your multiplicative factor here. This is learning to learn at test time, by the way. So they're very similar. The only difference is instead of updating it with your key value outer product, you're updating it with this gradient that comes from the keys and the values. So I feel like there's something there. It seems like this model is much better than the other model, and it kind of self-controls. It kind of controls itself in terms of the magnitude. Like, it seems pretty stable from what I can tell online. Like from things I've seen, RWKV uses this, and RWKV seems to be pretty good. I hope they release a paper soon. But RWKV uses this exact same idea, so that should mean that it's pretty stable. And I wonder if that has to do with the gradient, or if the gradient just has special properties that keep this hidden state under control. Because this is just a linear update rule that you're doing, and this is just a linear update rule that you're doing. The difference is this is just a gradient that you're taking, while this is just a naive outer product. So I feel like there's something there that this has that the normal linear attention update rule does not. Some property, just a thought, but I just wanted to mention it. But that's the difference between those two, and this forward method here is the exact same as the inner product here. You take the queries and you multiply it by, you do an inner product with the weights here. So that is learning to learn at test time, kind of a diagram that I wanted to draw to give more of an intuition on it. Not a massive difference, but it seems to make a big change in terms of stability and things. So here are the two diagrams. This is learning to learn at test time, and this is Titans. Essentially, you add this, you take the momentum. So you're essentially adding this momentum part here, and you're adding another control parameter here. So you don't change it a ton. So the gradient here is instead updating this momentum matrix here, this momentum hidden state. So this part here is exactly the same. So instead of updating the model directly, you're updating this hidden state, this momentum hidden state. This here is the momentum parameter. This here is the normal learning rate that we had before. So this is just the momentum, and the momentum is used to update the model, where this here is another added part that wasn't here, which basically is a forget gate. So very similar to the model that we had in learning to learn at test time. It's just you add this part here, and that's the difference. The output procedure and the input procedures are the same. It's just you have two hidden states now. Eventually, maybe we'll just come up with another LSTM, because like this basically, like, we went from RNNs to transformers, and transformers are great because you have, like, they're great and not great because of memory. But then we went from transformers to RNNs using linear attention, and now we're slowly building this massive linear attention block, which is just a complicated RNN. So eventually, like, if we look at the evolution from this naive linear attention mechanism and we slowly go from here to here, eventually I feel like we're going to get back to an LSTM, and we're going to be like, an LSTM is a pretty good it has some pretty good it has a pretty good update procedure, and we should use that as our inner model. Jokes aside, yeah, this is what it looks like in a diagram. So this is the inner update rule that they talk about, and they talk about, it's inefficient, and in the learning to learn at test time, they mention how you parallelize this. So this is a mess here. I'm not going to talk about each part of this, but essentially, if you have linear attention, you have two ways you can compute it. So you can either, so let me draw out the matrix here. You have your queries and your keys, and you have your mask here. So you can either compute it by going down the queries and storing a hidden state, and basically saving the key value projection for every query that you have, and that would be your RNN procedure. So this is constant in terms of memory, but it's really slow because you have to do an iterative procedure. It sucks on the GPU. It's just not good for the GPU. So that would be our rule here. H at time t is equal to, it would be whatever learning procedure we want. So it would be h at time t minus 1 plus some function of the keys and the values. So this works for the gradient update rule, as well as the, because the gradient update rule is just like, the gradient is a closed form solution, so it's just a more complicated version of the key transpose value outer product. It's actually, I think this is it right here. That's our gradient update rule, I think. It's just a little more complicated, so that's what you have here. And basically you just compute this, and you do you iterate over your entire sequence, and you do a scan in CUDA memory, or in your CUDA kernel. Another way to do this is by just computing this entire big matrix here. And it's no more efficient in terms of memory whenever you're training your transformer. But whenever you're doing inference, you can go back to this procedure here, the RNN procedure, which is constant in memory. The problem is, if we're doing linear attention, you would want to have, since you have this linearity property, you would want to kind of utilize that during training. But if you do either of these methods, you either have something that's really slow that does use this property, or something that's really, really fast because it's just a single matrix multiplication that doesn't use this property in memory. So to get around this, kind of the go-to method is to block this by saying, let me draw this out a little bit better. This is pretty bad. There, that's better. Let's say we block it like this. yeah, I'll go in blocks of size 2, but it can be blocks of any size. And the idea is we're going to compute this block in parallel, so using the quadratic method, while we iterate over this entire thing. So basically, we're going to compute this part in parallel. So that would be our queries from token 0 to token 1. Yeah, so our queries multiplied by our keys from 0 to 1 transpose, and you get this block here, and you just do your normal attention procedure from there. And then what you do is you store the hidden state up to this point. So that's really easy to compute. That's just the keys and the values at time 0 plus the keys and the values at time 1. And if you're doing the gradient update rule, it's the same idea because remember, you're updating your hidden state with your gradient. So you just compute this part in parallel and you store your hidden state at this point. And since you store this hidden state at this point, that means you don't have to compute any of this right here because your hidden state stores all that. It's the same for this part of the matrix here. So then what you do is for your second block, you compute this in parallel, you then update your hidden state, and now you have this part. And you keep on doing that. So this basically gives you something in the middle where you have your parallel algorithm that is very efficient on whenever you're using a GPU, because it can do this inner product really, really fast. So you can get your outputs for your block really fast, and you can update your hidden state really fast. And then you iterate over your entire matrix here, but you're not iterating over everything. So it's something in the middle where you compute this in parallel, and you don't have to do a scan over this part of the memory. You just have to do a scan over the blocks. So scan over the blocks is much more efficient than a scan over every part in memory. So it's way more efficient if you do it this way because you're utilizing your CUDA cores. And if you make the block size equal to the number of CUDA cores, or not CUDA cores, but like threads you can allocate, which I think is 1,000 on like an A100 GPU, then that would make this quite efficient. Or if you allocate it to something somewhat large like that, maybe not 1,000, but something decently large, then you can use the number of CUDA cores or use the number of CUDA threads while iterating over your sequence. So you get the best of both worlds. And that's why this algorithm is used instead of the naive algorithm of either doing just the inner product and computing everything at once, or doing an RNN where you had to compute it step by step. This is something in the middle where you're doing some parts at once and iterating over those parts. So they mention that they do that exact same thing specifically for the model. So the model at time t is only updated for every block, and they call this, learning to learn at test time. Learning to learn at test time kind of called this batch gradient descent, because in a way, or I guess you are exactly doing batch gradient descent on the model. So the model looking at this here, let me erase a few things. So if we have a model at this time step here, we're going to use that exact same model for both these here. So for every part in the batch, you use the model right at the beginning of that batch for the next tokens in that batch. So if I had a model at time 4 and my batch size was 2, I would use that model to compute the output at time 5 and the output at time 6. And then I would update the model using the gradients for these parts here to get the model at time 6. But you can compute these in parallel because batch gradient descent that's how you do batches in parallel. So that's what you do. That's what they're basically saying here. They're saying the model at time t, they have this t prime here, which is this modulo arithmetic mess that they do. But basically it's this batch update where you can do the batch update in parallel using this here. And they mention that this is kind of the batch of the learning rates, this is the batch of the decay values B, and this is the batch of gradients here. And that'll give you your batch gradient update rule for the model at time t. So this is your batch update rule over the entire batch of B of your block of size B. Then you use this to go from one block to the next block. So you update your model using that. But remember, we added momentum. So they mention here that momentum is not updated blockwise. Momentum is updated within the block. So we have our model being updated from block 1 to block 2, but we're going to have our momentum be updated every time. So S at time 4 is updated to S at time 5 is updated to S at time 6. So that means that our momentum has to do a scan over the entire, the momentum has to do a scan over the entire block. So momentum actually does compute, does have to compute everything. But the nice part is you can compute the gradient in parallel. So basically you just have this recurrent scan that you have to do where your gradients are computed in parallel over the block. But you do a scan over your learning rate. What are these values again? These were the decay values. So you do a scan over your decay values and the batch gradients. They mention if you don't have your these values here, these decay values, temporal. So you just make them learned and it's the same value over the overall time. Then you don't have to do a scan and you can just do the a convolution like the SSMs because this isn't temporal anymore. So you just have to do a scan over the batch because you have this temporal weight decay parameter, but you can still compute the gradient all in parallel. So that's what they mention here. You compute the gradient blockwise and you update it blockwise or batchwise. And you can compute the batch in parallel, and you update your momentum at every time step, so not batch-wise. Yeah, so that is what this is saying here. If you are curious exactly how they do that, feel free to kind of read through this, all this mathematical notation. But that's the summary of that part. One thing I want to mention, whenever you are doing inference, let's say we have our model at time t and we have a block size, a batch size of say 3. You would use your model at time t. So like, let's say we want to predict the next token. So you use this to predict the next token at time t plus 1, but you wouldn't, I guess you have your momentum here S at time t. You'd only update the momentum to S at time t plus 1 after you get your new token prediction. And then you would get your output at t plus 2 after you get your first token prediction. But this output uses the model at time t again, because remember, we didn't update our model at all. And you save this information here for updating your model at time t. So you're saving the gradient that you got for the output at time t plus 1. To update your model in a batch format. So then once you get, so your momentum is used to get this, and then you get output at t plus 3, which you then use your model at time t again. You use your momentum at time t plus 2. And finally, you update your model to t plus, I guess this would be 4, using the gradients that you obtained for every output here. So for your entire batch and the momentum parameters here, S at time t plus 3. So you basically have to store this extra information until you reach a new batch whenever you're doing inference. Because while you're doing inference, you don't have your entire batch, so you can't compute it all at the same time because you're doing, well, inference. You're slowly generating this batch. Just a side note I wanted to point out, because immediately I'm like, oh, how do you do inference with this? But you basically just have to store this batch information. So yeah, that is the internal model that they talk about. Let's talk about the and then they make this big point about persistent memory, which is just an attention sink. So they concat these tokens to the beginning of the sequence because it is persistent memory, but this is just an attention sink. You just add these learnable tokens that, because the attention can throw stuff away into there. And you just have these tokens that aren't used for your output. So they call it persistent tokens though. So you'll see this here, this notation, and this just means concatenate the learned persistent tokens, concatenate with the input here. And they say that here. From the technical perspective, these learnable parameters at the start of the sequence can mitigate such effects by redistributing the attention weights more effectively. And I'm guessing one of these is the attention sink papers. I didn't actually look. So let's talk about how to incorporate the memory into the models. This is where it gets very, very ambiguous, and they don't explain everything well, and the notation is a mess. And I tried my best to break it down, but I don't have every single detail, and I don't think they include it. I could be missing something, but I'm not certain. I don't think they provide any code either, so it's not very helpful whenever you're breaking this down. But basically, they have three models. They have a model memory as a context. They have gated memory. They have memory as a layer, and then they have a fourth one as well. Here, memory without attention. And basically what they're going to do is they're going to apply quadratic softmax attention and this linear momentum attention that they created, and they're going to combine them in a few ways, while this one only has the linear attention without the quadratic attention. And they're going to compare them and see how they work. But they're all very similar. Basically, you can either iterate over your entire sequence. So you want to iterate over your entire sequence, and you have the memory that they propose, this momentum memory, the learning to learn at test time memory, that's going to store information over your entire sequence, while your quadratic, your softmax attention is going to only work on segments of your sequence. So if we look at memory as a context, you start off by extracting information from your memory at time step t-1. So I think the queries come from the segment information. Yes, they do. Yeah. So basically, you have a segment at time t, and this segment here is they say they break it up into B blocks of size C. So your segment is the C by D matrix, where C is the block size. So you basically have C tokens that you're computing at once, and you're extracting memory from these C tokens. I'm thinking they use this as the batch. So they use the C part as the batch to do the batch gradient descent on, or at least that's what I'm thinking. I don't know how big they make this because I don't think they mention it at all. But that would be my guess. You can make the C size how big you want your batch to be, so that you can compute this efficiently and do your batch gradient descent as efficient as possible. You then concatenate here. These are your persistent tokens, the attention sinks, your outputs from the memory. So you basically extract your memory from whatever you had over your entire sequence, and S at time t. So this is just your input tokens. And using all of these, so using your persistent tokens, your memory tokens, so this is long-term memory, and they call this kind of, did they call it short-term memory? Maybe. So your long-term memory, basically what you've remembered over the entire sequence, and your tokens of the segment, your segment tokens, you concatenate all of them, and you throw that through normal softmax attention, and you get your output Y at time t. And I just mentioned you remove the attention sinks here because those aren't needed at all. You then update your memory. So this part here is weird. They say, note that in the above, we are updating the weight of m at time t-1 through forward pass. I don't know what that means. Maybe somebody can explain what that means, but our memory here is of dimension d by d. It is a matrix, or at least like that's the projection you end up getting. Even if it's an MLP, it goes from size d to d. If I update it with the forward pass, which is of size 2c by d, it doesn't work. So I'm going to assume they meant you are updating n at m at time t normally, and you do that whenever you do a forward pass. That is my guess. So this here mathematically doesn't look like it, but I think what you do is you update the memory using y at time t. So you update it normally, and I'm guessing this is your batch size here, or at least you can segment this into multiple batches if you need to. So you do the normal update rule that we described above, except on yt, where yt is the output of the attention, where the input to the attention is the memory at time t. So this is all our past memory, our current tokens, and the persistent tokens. And basically, you have this memory used as a gate. So after you update it, you then do the output rule here using y at time t and y at time t here. So basically, you use it as a gating mechanism for your output of your attention here. So you use the past memory as the input to attention, and you use the updated memory as a gate here. And that's what they call memory as a context. This is kind of the most complicated, and then they kind of remove parts to it. So they have a diagram up here where they say, oh, you take your sequence, you extract the memory from there, you combine your persistent tokens, the memory from that sequence, and the current sequence here. You concatenate all those. You throw it through attention, you update your memory, and then you get your output via the output of attention and the new memory doing inference on the output of attention. Yeah, so that's what we have here. And then they also have this other diagram here, basically showing how that kind of works in a way. Yeah, but basically it's just your attention being computed locally while your RNN is going over the entire sequence. Gated memory. This is slightly simpler, and essentially it's you only use your memory as a gate as opposed to as an input. So notice that our input here is not just it's just two parts. We don't get anything from our memory. So we have our persistent tokens here, our attention sinks, and our input. We feed this through our sliding window attention, which is essentially what you had above. I don't know how the two deviate. I think this is also just softmax attention. I think it is. Sliding window attention with prefix. That's what it is. So still like softmax attention, but windowed. And then you have your output, and you use your memory as a gate. And note that this comes from the input. So you take the input, you throw it through your memory, and you get this gate here, which directly gates the output of your sliding window attention. And they mention this part here. The gate is we normalize the output y and the memory gate using learnable vector valued weights. I think here they update the memory using these tokens, and then they do the gate. But I am not sure. They could, yeah, I'm not exactly sure, because this is all they have here for me to go off of. That is my guess, though. They update the memory with x at time t, so the current inputs, and then they do inference with x at time t to get the gate, and then they apply the gate to y. I can go back to the diagram up here. So sliding window attention, and you add your long-term memory here, which basically gives you context of the past, but it's decayed, so that's why it looks like that, and you have your attention sinks. So memory as a gate, and they have another diagram here. You have your sequence, you can concatenate it with your persistent tokens, You then, yeah, I think you update your memory with the input, and you get your attention output with the input, and you use this kind of use this as a gate, and then you get your output. So that is gated. Memory as a layer. Here, they basically have disjoint parts. So you know how we usually have attention, MLP, attention, MLP? This is the same idea. Instead of having attention, MLP, you have memory, so long-term memory, and then attention, long-term memory, attention. So here you have your persistent tokens, you have your sequence, and you concatenate the two. You feed this into your memory, it updates, and you get an output. So normal learning to learn at test time output that we've seen before, and then you feed your output through sliding window attention, where this is some window size, probably some very large window size. And they show that here. You take your inputs, you throw it through your memory, you get an output from your memory, throw that through attention, and then you do this again. And that's memory as a layer. And they mention the main drawback of this design is the power of the model is limited by each of the layers, and so it cannot take advantage of the data processing of attention and the neural memory module. And we'll see, well, I'm not going to show the results too much because, of course, they get state of the art, but it doesn't work as well as the other two. And memory without attention, so this is just linear, the linear update gradient rule that they had, the momentum update rule. If you just use that, it also doesn't work as well. Architecture details. So in our implementation, we use Silu the Silu activation as the nonlinear activation for computing the QKV, and normalize queries and keys using the L2 norm. I find that kind of interesting because that essentially removes all the magnitude information, and if you do that for normal softmax attention, it doesn't do as well. That's just something interesting, but maybe that's because you're doing this this gradient update rule instead, so maybe that doesn't matter. Following, they mention here, they use a 1D depth-wise separable convolution layer after each of the query key value projections. So that's what we saw in, I think it was H3 and in Mamba. Basically, all the linear attention mechanisms use that. It's kind of this time-wise sharing of information, this local time-wise sharing of information. Gating, they say normalization and gating with a linear layer before the final output projection, so as you would expect. And then they have experiments. So I guess I could show you the experiments. Of course, they get state of the art, but yeah, if you look at them, it does really, really well compared to things like Transformer++, which is just the quadratic attention transformer. They scale it up quite large to, well, I say quite large to kind of like a reasonable size, I guess, 760 million parameters. I wish they did larger, but they scale it somewhat, and never mind, that's not large. They scale it, and I was looking at the 30 billion. I'm like, oh, that's decent. No, they don't scale it that large. They have different scales that they use, but they don't scale it that large. But if you look at the within, so they basically get the best overall for most tasks, because of course you do. That's what you put into paper. If we look here, we have the first two I talked about are usually the best, while you have LLM and MAL, memory as a layer, and just linear attention. So LLM is just the linear attention. Then those two don't do as well as the other two. Here, they have a long sequence length in a few shot fine-tuning setup. That's what you would expect, though. You would expect this to have a pretty good sequence length because it has this linear attention mechanism that can store information through the entire sequence. So that's cool. And the accuracy drops off, which is pretty cool. They mention here in the needle in the haystack that it does quite well. I think that is this here. It does pretty well on needle in a haystack, and that's always the problem with linear attention mechanisms. Like we can see Mamba, it doesn't do too well. Like at 16K, it does 16K time steps. It does pretty like 0%. So other linear attention mechanisms have trouble. They claim that their linear attention mechanism can do the needle in the haystack task. Is this because of data leakage or something? I don't know. I don't want to make any claims about it, but I'm just saying usually models are not that good at needle in a haystack because they have to know what to save in their hidden state before they save that in their hidden state. So a little suspicious, but they show that nonetheless. So yeah, not going to make any claims on that. Just it is. They show it scales to 760 million parameters. They show it's pretty good at like time series forecasting here. Neural memory. They show all models scale linearly with respect to the context length as expected because it's using linear memory and it's using windowed quadratic attention. Here they show it does pretty well on DNA modeling, so that's cool. They show it's efficient, and they do ablations. I think the ablations are kind of interesting. If we look at the ablations, we can see that there are three really important parts. So this is, this is LLM. So this is if you just use their linear attention mechanism. These are the two, the first two I talked about, and this is the third, memory as a layer. So you can see it's quite a significant improvement if you use softmax quadratic attention. But if we just look at normal linear, the linear method they have, and we look at the other parts here, let's say we replace their method, so this their update rule, their gradient update rule, and we replace that with a linear attention mechanism. I don't think they mention what they replace it with, but if you do that, you get a much lower score. Interestingly, if you don't have any weight decay, it also does terrible. Like it's much worse than if you have weight decay. So I find that interesting. And that means that the model really utilizes this decay, this decay in the hidden state, so that current information is more important than past information. So I find that really, really interesting. And then momentum, if you add momentum, it does a lot better. So that's interesting. Persistent memory, they make a very big deal about persistent memory. It doesn't do much at all. I kind of find that funny, and the convolution helps a little bit. The convolution after the query keys and values. Like it doesn't help like at all. I don't know why they make such a big deal about persistent memory. I just find it kind of funny. So yeah, that is this paper. It's not Transformers 2. It's not the next big thing. It's cool. I think the research is interesting. I do not think it should be as hyped up as much as it has been. But yeah, I don't want to take away from how cool this. Like I do think it's interesting. I think the research is cool. There's just too much hype around it. I don't want to take away from what they have done in this paper. But yeah, that is Titans. That's the paper.